Good afternoon, everyone. It's great to see you all here at the DeSouza Award ceremony. It's my distinct pleasure to give you a little background about the award and how it came about and what it serves to be in terms of personification. Um, Russ DeSouza Award is always given to individuals and honors people whose energy, expertise, and active involvement enabled the Unidata program to better serve geoscience. Honorees personify Unidata's ideal of a community that shares data, software, uh, ideas through computing and networking technologies. And I wanted to say a few words about my former colleague, Russ DeSouza. Um, Russ DeSouza joined the Unidata Users Committee the same day I joined the Unidata Users Committee in 1989. So we were cohorts in the first group of UserCom members, and that committee was newly created to help then policy committee, which is now called the Strategic Advisory Committee, to be more connected with the user community in terms of the needs, in terms of perceptions, both on the data side as well as on the software and tools side. Russ DeSouza was a professor at Millersville University at that time, and at that time, Millersville University was not the powerhouse that it is today. It was a relatively small program, and Russ was so inspired by Unidata that he wanted to bring Unidata capabilities into his classroom, and eventually they built up a very successful program, which is now one of the top programs in our field. That work was continued later on by Rich Clark, who is the AMS president, as well as a longtime member of the UCAR Board of Trustees. Russ and I worked together for several years as members of the Users Committee. And one of the coolest things he did was, back then we had to decide which sector of the GHOST satellite imagery we should push to our community on a daily basis, because bandwidth was very limited. We didn't have the IDD and internet transport. A lot of the data, or all of the data, went through a satellite broadcast system, which was relatively slow. So we had to be very picky or choosy in terms of how much data to push and what sector of data to send to our users. So Russ worked with his students to select the sector of the day, for each day. So the students would get together, look at all the weather action, and say, this is the most important thing in CONUS US, and so they will send that centroid of that sector to Unidata staff, who will then create the sector to ingest into what was then called University of Wisconsin, broadcast. And one thing led to another, and the students really got into Unidata tools and technologies. He then moved on to the Unidata Policy Committee, which is now called the Strategic Advisory Committee. And after serving on the Policy Committee for a couple of years, he developed melanoma, which was malignant. And about a year later, he had to step down from the Policy Committee and also retired from Millersville in 1997, May 17. And literally 3 weeks later, on June 6th, he passed away. But his legacy lived on not only at Millersville, but with the Unidata program. And Unidata created this award because he was the personification of helping the community with the work he was doing, to pick the sector and improve Unidata capabilities. And since 2000, we have been giving this award almost on an annual basis, although we have had 1 or 2 gaps over the years due to COVID and other reasons. And today we are honoring 2 extraordinary individuals who have helped the Unidata program to establish the Unidata Science Gateway and leverage the capabilities of cloud computing on the Jetstream and Jetstream 2 infrastructure that is an NSF-funded cyber infrastructure. With that, I'm going to just turn it over to Kevin to say more about the individuals. But congratulations, Andrea and Jeremy. I see that you're online. Congratulations to you as well.
All right, good afternoon. I'm Kevin Gobert, the outgoing chair of the Unidata Users Committee, and it's my pleasure to present our awardees today. So the 2023 Russell L. DeSouza Award is a little different in that we're honoring 2 individuals from different institutions who have been supporting the Unidata community in very similar ways. Andrea Zonca from the San Diego Supercomputing Center and Jeremy Fischer from Indiana University have both been vital contributors to Unidata's Science Gateway project through, among other things, their work in porting the Zero to Jupiter Hub with Kubernetes project to the NSF Jetstream cloud. And we're happy to have Andrea with us in person today and Jeremy remotely from Indiana. When the COVID-19 pandemic first hit, Unidata pivoted to using the Science Gateway resources to deploy Jupiter Hub servers in support of remote learning experiences for university students. Jupiter and Jupiter Hub technologies allow users to access pre-configured interactive notebooks for instructional purposes. In partnership with the university professors and educators, Unidata equips these servers with pre-configured Python for Atmospheric Science Environments, or PyAOS. Since the spring of 2020, Unidata has provided access using these resources to close to 1,400 students at 19 different universities. These achievements were made possible by the efforts of Andrea, who forked the main Zero to Jupiter Hub project and reconfigured it with the help of Jeremy to run on Jetstream. At the same time, Jeremy has supported a wide variety of other Unidata resources running on the Jetstream platform, from a publicly accessible cloud EDX server to threads and Ramada servers used in a variety of contexts. Both Andrea and Jeremy provided the Unidata community with their extensive expertise at the hardware, operating system, and software levels to ensure these servers run smoothly. When problems do arise, as they inevitably do, Andrea and Jeremy have quickly intervened to resolve issues to provide workarounds. Taken together, these activities have had an enormous impact on Unidata's community of students and researchers by making Jetstream resources available in ways that are truly useful, including myself, and I'm so entirely grateful from that pandemic pivot. And so we give the DeSouza Award honorees a physical plaque as a small token of our appreciation, and we're happy to be able to hand it to Andrea in person here today, and Jeremy should have his at home, and so we'll have Andrea come up. There you go. And that I'll just speak a little bit about what the award description states. And so for your dedication, enthusiasm, and inspiration that truly reflect the goals and ideals of the Unidata program, we present Andrea Zonca and Jeremy Fischer with the 2023 Russell L. DeSouza Award. You exemplify these ideals through your ongoing efforts to help educators, students, and researchers take advantage of cloud computing technologies and workflows using resources provided by the Jetstream and Jetstream 2 programs. We especially appreciate your contributions to Unidata efforts to bring cloud-hosted Jupiter Hub resources to classrooms during the COVID-19 pandemic. With your help, Unidata has been able to serve over 1,000 students in this way to date. We offer this award in recognition of and appreciation for your outstanding service to the Earth System science community. Join me in congratulating Andrea and Jeremy on behalf of the community, and we now welcome them for their presentation.
All right, I just wanted to introduce myself. I'm Jeremy Fischer. I am employed by Indiana University for the last 8 years now. 8 years. I've been involved with the Jetstream and Jetstream 2 projects, which are NSF-funded clouds. I am now the manager of the Research Cloud Infrastructure team at IU, which manages Jetstream as well as another internal cloud. And I'm a co-PI on the Jetstream 2 project. Without further ado, I'll jump on in. So next slide, please. So a little bit about Jetstream 2. I'm going to cover what Jetstream 2 is and what it's capable of, and a little bit about how Unidata has used it in the past and into the present. And then Andrea will jump into more of the current efforts going on today that he's been involved with. So Jetstream 2 is a National Science Foundation funded cloud environment. We are the first production science cloud for research and education. We have a focus on ease of use, as well as providing environments that we call programmable cyber infrastructure. So you can make it do what you want, when you want, and how you want. And with Jetstream 2, we're building on the success of Jetstream 1. So previously, we had 63 science gateways, and over the 6 and some change year span of the project, we supported about 183,000 people indirectly and about 16,000 people directly. We had a nice uptime average, as you can see here, but the goal was basically to provide a platform that's been kind of missing for education and research purposes. Next slide. So a little bit about our capabilities. We are about 400 nodes, all EPYC 3 Milans, 128 core nodes, with 512 on most of the nodes. We have 90 GPU nodes, each with 4 A100s. And then we have 32 large memory nodes that have a terabyte of RAM each. We're not doing any hyper-threading or over-subscription with this. It's straight RAM or straight cores, so you're not sharing cores with anybody. There's all the floating point is available to you as it wouldn't be with hyper-threading. We also have 4 regional nodes in addition to our primary cloud at Indiana University. Those are available by invitation and request at Arizona State, Cornell, Hawaii, and then Texas Advanced Computing Center. We took a page from our HPC brethren, and we have a shared software library that is manageable with LMOD modules. We do feature Jupyter hubs, virtual clusters, and orchestration. We're working on improving the orchestration features as we speak. And we do have a commitment to uptime. Our last reporting to NSF was a 99.87% available uptime. We're getting ready to redo those numbers again. And unfortunately, due to a power outage or two that were beyond our control, they won't be quite as good, but they'll still be pretty good. And then also in storage-wise, something different between Jetstream 1 and 2 is a lot more storage, 8.2 petabytes usable in hard drive and 4.4 usable in NVMe. Next slide, please. So there are multiple touch points for getting into the Jetstream 2 cloud. So science gateways are the way we serve the broadest number of users, and including Unidata's efforts with their Jupyter hub. We have Exosphere, which is the more common graphical user interface that most of our direct users use. And then we have the Cacao user interface, which is mostly centered on automation, and then the built-in Horizon and OpenStack command line interfaces. And then all of that ties into the Access accounting system and Access authentication services as well. Next slide, please. So sample use cases for Jetstream, and there are a lot. I talk about the number of fields of science in one of the slides, but in terms of actual use cases, it's astounding how many different things I've seen come through over the years. Science gateways are obviously a prime mission, as is education support. So whether it's doing direct coursework or doing trainings for research professionals, it is one of our primary functions to act as the platform for helping educate others. Of course, research is a primary use case, and infrastructure as a service in support of that research. Domain science interactive computing is huge. It's where we see a lot of users that don't have a home with traditional HPC. A lot of times because they need really long run times or just kind of get lost in the HPC shuffle. Jupyter hubs and notebooks are a prime use case, and then machine learning. There's probably a little bit about AI in the news these days. So people that are starting to do training work with different sorts of data, and especially we're seeing a lot of natural language training sets. And then, as I like to say in the bottom there, your use case here, because there's always the use case that we haven't thought of and didn't plan on and has found us and wants to work with us. So it's really the sky's the limit. Next slide, please. So talking about gateways, again, as I mentioned, we have a lot of gateways on Jetstream, and they serve a lot of users. Gateway web hosting is probably the most common use case, where they will provide a front end for either doing local computing or computing using another HPC resource. Those probably are the largest section of our gateways in use right now. Data sets and database for backing scientific research is another growing section. Integrated Jupyter hubs is definitely one we're seeing growing, and it's kind of prompting us to look at other ways we can make Jupyter hubs more accessible to more people. We look like we're going to do a partnership with Chameleon Cloud on using their standalone Jupyter interface and also integrating that with Jetstream as well. Elastic virtual clusters are one that we support. There's a small but very dedicated audience that likes to run their own small Swarm clusters. Sometimes it's in combination with a gateway, and sometimes not. But those are some of our use cases for gateways there. Next slide, please. Again, about elastic virtual clusters. So for the people that want to run their own Swarm-based cluster, we have an on-demand one-click launch for that. So it's built on OpenHPC and provides a mostly lightweight HPC stack and gives you a default 3-node cluster, which you can expand and have dynamically grow and shrink as needed. There is mounted persistent storage available to you, and it makes it so like you are using any other cluster anywhere else, only you have control over it. So a lot of people that are using those are either doing small workloads of their own, or they're doing MPI development or testing and want to have a place where they can simulate what happens in a real cluster. Next slide, please. So some key statistics. So since we went into early operations, we've had 3,200 users on Jetstream 2. We've had about 198,000 users via Science Gateway, and that's actually apparently over 200,000 now, because I didn't have the Unidata number on 1,400 users, so I'll get to add that in. We've had 74 fields of science represented on Jetstream 2, and at any given time, we have between 300 and 400 projects using the system. So we are committed to growth and have some room to keep going on to help support even more research and education. Next slide, please. So using Jetstream 2 as part of our contract with the National Science Foundation, we are completely allocated via access. So you have to be on a valid allocation before you can use the system. The upside is that there's no cost in money. It's just a little cost in time. And most of the time for that is fairly simple, unless you're going for one of the largest allocations. So next slide, please. So Access is another National Science Foundation project. It is the replacement for Exceed. It is basically a virtual organization that provides the holding organization for HPC resources and cloud resources for the national cyber infrastructure. So to get to Jetstream 2, you have an account with them, and then you apply for an allocation with them to use our system, and then you can do your work. Next slide, please. So accessing Jetstream 2, there are a variety of interfaces like I talked about. You can see the Exosphere interface up on the left-hand side and the command line. Those are probably the two most common ways that people use the system. Exosphere is meant for to get out of your way. So it's a handful of clicks to have a virtual machine up and running of your very own. And then the command line is for part of your users that maybe want to script things. It allows you to do things in a more programmatic way. There's also a Python SDK behind the scenes that you can use to do all the same things that you can do from the command line as well. But the other two interfaces that I showed there are Horizon, which is the lower right, which is OpenStack's built-in GUI. It's complete. It's not very user-friendly, but everything is there that you would ever need. And then Cacao is on the left-hand side at the bottom, which is still in beta, but it's very uniquely geared for doing Kubernetes and doing Terraform-related activities with Jetstream 2. Basically, it's all built around using Terraform templates and doing your own launches. And we provide a handful of templates for folks to get started with, including a Jupyter Hub template and a basic Kubernetes template as well. Next slide, please. So using and preserving VMs, pretty much you can install anything you want. You get root. So with that great power comes great responsibility. You are generally limited to Unix, to Linux. I note here there be dragons because somebody always asks about Windows. We do provide a Windows server image. I'll give you fair warning that our entire team are all either Linux admins or, like me, started with the various Unix systems that were out there many, many years ago, and try not to ever touch Windows. So support there is a little bit limited, although our partners at Cornell work with us as needed to help support Windows on Jetstream 2. We do try to help people have a consistent way to reproduce their workflow, whether it's doing local snapshots or having better practices of doing, pulling from a Git repo or pulling containers as well. Next slide, please. Allocation and usage considerations. So we generally don't take downtimes for upgrades. We do things on a rolling basis and try to keep everything live while we're doing updates. So we'll take a hypervisor out of service, we'll do the updates, we'll bring it back, and we'll move on to the next one and continually roll the cluster that way. In general, if all things are going well, people don't notice. The one downside that we found is thanks to some failed functionality from NVIDIA, we can't do that with our GPU nodes. So we actually do have to coordinate taking those offline for work. So that's an unfortunate thing that we were promised would be fixed, and it's not going to be fixed. You also get persistent IP addresses for the course of your allocation if you would like it. So basically you can draw an IP address and use it as long as you have an active allocation. There are no runtime limits, so we don't tell you, when you can run your VMs. As long as you have an active allocation with core hours available, you can keep using your allocation. And there are no limits. So if you can justify it and we can provide it, we're going to provide it. We do have allocations that request millions of core hours a year. Unidata is in fact one of those. But if you can justify having it to the panel that reviews them, then it is yours for the taking. Storage allocations are reasonably generous. I know when talking to atmospheric sciences folks, what is reasonable to one is not nearly enough to others. We default to 1 terabyte to start out, generally up to 50 terabytes. We do go a little bit larger for read-only data sets on our spinning disk. But compared to Jetstream 1 and where we started, it's been a world of difference. Next slide, please. I got behind. So here are some links for getting help. So our Jetstream 2 documentation, the access documentation. I will be putting these slides up on the jetstreamcloud.org site as well, so you'll have them as a reference if you need to get to them. But hopefully we're fairly easy to find. Searching things out for access is a little more difficult. If you try to Google access, you can only imagine how difficult it might be to find things. So hopefully you can find them all from our slides. And next slide, please. And then a little bit about Unidata before Andrea starts in with his section. So Unidata was one of our earliest adopters on Jetstream 1. We began our early operations in June 2016. And I believe Unidata was on in June 2016. Our I worked early on with Julian Chastang and Mike Schmidt and a couple other folks. There was a combination of API side. In fact, Unidata was one of the earliest API users on Jetstream 1. We actually had not intended to give API access for the first year. And Unidata was one of the folks that came along and basically said, we need to do some things programmatically. And so it kind of hastened us into that mode as well. And then Mike also ran a few things on Atmosphere side as well. It evolved mostly all into API side as we moved into Jetstream 2, especially with the auto-scaling Jupyter Hub deployment. Andrea had developed a set of tutorials for Jetstream 1 and evolved them over to Jetstream 2 as well. And it was that work that Unidata's Jupyter Hub is based on, I believe, and has grown over the years with, and has changed and adapted over the years. A little bit about Unidata's usage. So starting when we started recording data in 2017, usage data, Unidata used about 4 million core hours over the first 3 to 4 years, expanding to between 5 and 6 just before Jetstream 1 ended. And then now on Jetstream 2, after our first year of operations, Unidata has used about 8 million core hours between the three resources, between Jetstream CPU, GPU, and large memory. So it's definitely a large consumer of resources and hopefully doing a lot of good with those resources. Right now, when I looked in doing these slides, there are over 100 running instances on Jetstream 2. About 30 of them are labeled test, which I think is related to some updates of the Jupyter Hub, but lots of eDEX and threads and other things running as well. So I believe that concludes my portion of the show. Next one, Andrea.
Thank you, Jeremy.
Yep.
Okay, can you hear me? Also online, people can hear me? Yep. Okay. Yeah, so I wanted to start with this slide provided by Julian. About what Unidata has been able to achieve thanks to Jetstream resources and thanks to the kind of deployment that we've been doing for a few years now. And so you see a lot of users, university workshops, and we keep updating and adding more functionality to those deployments to allow students in particular, or researchers, whoever is the user on the platform, to be able to do more tasks. And so what I want to do right now is I'm going to show you what are the current capabilities of the systems, the kind of the system that is currently being used by Unidata, but I'm also going to show you other capabilities that I have deployed on this platform for other projects. And then so that you have an idea of a wider view of the different capabilities, so that you can maybe think about deploying other services on the platform. Okay, so let's start with at the basis of everything is the deployment of Kubernetes. Okay, so we want to be able to deploy services on top of Jetstream, and we want to be able to handle these services distributed over several virtual machines. So we need a system that can help us making this distributed deployment easier, and that's Kubernetes helps us with that, because can provide orchestration of Docker containers running across multiple machines, and then handles all the networking, handles logging. So we have a central point where we can see the logs of every service that's running, and helps with resiliency. So if one node goes down, then the service that was running there is just going to spawn on another node. Okay, and then the most important application that we deploy on top of Kubernetes, it's of course Jupyter Hub. Okay, And so let's take a look at the structure of this. So you see, we have multiple virtual machines on Jetstream, and those virtual machines have a Docker environment, and the Docker environments across all of those machines is managed by Kubernetes, okay? So you have your Jupyter Hub container, which is a Docker container, and thanks to the tutorial that I have deployed and that, for example, Julian is using, you can deploy all of this infrastructure on Jetstream, and then you can interact with Kubernetes to create services, okay? So our first service, for example, here is a Jupyter Hub container, and so this Jupyter, and you define this at a very high level. So you have a command line interface to Kubernetes. You tell Kubernetes, please deploy Jupyter Hub using this image, and this is going to deploy your Jupyter Hub instance. And then it's also going to take care of all the networking for you. And so when a user then comes in and logs to the Jupyter Hub instance, the Jupyter Hub itself, it's also talking to Kubernetes. And so it's going to ask Kubernetes, please launch a user container somewhere else on the system. And so now we have another container, and this is, for example, a container that contains all the Pi, AOS, all the software stack for atmospheric sciences, so that the user can, so that all the students in a class or in a workshop, they have a consistent environment with the perfect version of all the software packages, and they are sure that everything's going to work. Okay. Yeah, and then all this is routed transparently back to the laptop of the user. Okay, and then if we have another user comes in, same thing happens. So the user gets the Jupyter Hub, authenticates, and then Jupyter Hub asks for, and all of this is handled automatically. So Kubernetes automatically checks where there are more resources available on a node, and then it's going to spawn that the service, which in this case is a Jupyter notebook with all of Jupyter notebook with all of the kernels in any language that you have available in your container. Okay, and so let's take a look on how this works on a live instance. So you see, you get to your Jupyter Hub, you authenticate. We generally use GitHub authentication, but there are many options. And so what happens here, you see, we're connected to Jupyter Hub, and this is spawning, is waiting for a container to spawn somewhere on this cluster. And then once this is ready, you have your Jupyter Hub. So you see, this Jupyter Hub is not running in my browser. Okay, it's not running on the head node, but it's running somewhere in my cluster of machines, and then it's going to be proxied all the way back to my browser. Okay, and so students connected here, they all have a consistent environment. Okay, and so now, and so they can do computing, but they can do computing on one node. Okay, and so they can use maybe multiple threads, but still they are limited to one single machine. But now what we can do is we want to give them access to more computational resources, more memory, more CPU. And so what we do is we can use this Python package, which is called Dask, which is a way of simplifying distributed computing. So basically, if you are familiar with Python, with NumPy, it looks a lot like NumPy, but can run also distributed on more different machines. So you describe the computation in a very easy way with similar interfaces to NumPy. So you want to call the mean of an array, you do .min, this kind of operations, and then you can use the standard math operations between arrays, and this runs in parallel across your machine. So this is a great way to introduce people to distributed computing, or to have people in a maybe in a scientific group, they need to analyze a lot of data. Those data do not fit, of course, on a laptop. And then you can run distributed all over multiple workers. Okay, so what happens in this infrastructure is that Dask gateway is another service, is another container running in the same environment handled by Kubernetes. And then the user from their notebook, they can request a cluster of workers be spawned somewhere in your cluster of machines. And you see here a Dask, and now we have a Dask cluster. So the Dask cluster is composed by a scheduler, which is coordinating the jobs between the different workers, and then the workers. And so the workers are the actual computational, is like having multiple kernels that are running distributively across your cluster of machines. And so you could process terabytes of data easily with this kind of system because the data is going to be distributed across all of your workers. And so instead of having 2 workers as they are here, you can have 10 workers, 100 workers, and so on. Okay, and so let me show you a quick example of how this works. Okay, so you are in your Jupyter notebook, and you say, I want 2 workers. You see here, I am connected to Dask gateway. I'm asking for 2 workers, and now I have 2 workers that are available, and also my Dask client is one of the best features of Dask is this dashboard. So basically, in the dashboard, you can see in real time what the different workers are doing on your machine. So let's say that you have some simple computation. So you have a random array, which is a matrix, and then you do some computation like this. You take the square, you see it's just some standard math operations like you would do in NumPy. And then you call compute, and this is, you see it's running and it's showing you live what all the different threads on your cluster is doing. And so the red is communication and the green is computing, okay? And so if you have, for example, a algorithm which is running poorly, it's going to have a lot of communication because maybe you're not balancing computing enough. And this is a great way of understanding how your distributed computation is running, which usually is very, very complicated if you're familiar with distributed computing. Okay, and okay, very good. Okay, if you want to learn more about this, I presented a tutorial, a 1 hour, 1 hour and a half tutorial at Gateways 2023 last week. It's available on YouTube. I have the link later on, so you can take a look at that. Okay, and then another great features that we can use from the Jetstream system is object store. So object store is a distributed data storage, which is similar to Amazon S3, okay, where you can, and so instead of storing your data in a standard volume, in a standard POSIX file system, you have this ZAR format, okay? This is like a replacement for NetCDF, which is specifically designed for distributed computing. So stores your data in chunks. And so once you want to access the data, you can access them in parallel because you can access from different workers, can access different chunks, all of it in parallel. And so you can have a extremely efficient, it's basically the equivalent of a parallel file system for cloud, okay? It's the same thing you would do with an MPI parallel IO on an HPC system, but on the cloud, okay? And so here you can have your Dask workers that are reading in parallel by object store, which is a separate service which is run by Jetstream. So you don't, you're not managing that. You're just a user. You dump your data on this object store, and then you can read it back extremely efficiently. Okay. And then another interesting feature is that we added the capability of running on GPU nodes. So this is complicated because, of course, we are inside containers, so you want to make sure that your GPU is accessible through from the container. And so I have a tutorial on how to the small modifications to do to our standard recipe for deploying Kubernetes. And so you could have Jupyter, and I have an example of having Jupyter Hub where the user can log in and they can run TensorFlow using on your GPU nodes on Jetstream. Okay, and next I'm going to show, and this is basically all things that Julian is already using. And then I have a few more, which some of them, okay, I want to show you a bit more capabilities that we have so that you have a broader view of what is doable. So one of them is a very common use case is that you want to share data across all the users because of course there is no shared file system like you would have in a supercomputer, right? And so if you want to have a volume which is accessible by all of your pods, all of your Jupyter users, you have a couple of options over here, and I have different tutorials. So those tutorials, they have step-by-step instructions on how to deploy this. And then I have a GitHub repository where I have all the configurations files that are needed to deploy this. So it's pretty easy to follow those tutorials and have this capability enabled. So one of them is using Manila. So Manila is a service by Jetstream where they basically you can instantiate a NSF server which is managed automatically by Jetstream. So it's very convenient because you don't have to handle it yourself. But if you want to need more flexibility, then you can also deploy an NFS server yourself. And so this is just going to be another container on Kubernetes. So you see, you're using Kubernetes to manage all of your services together. So it's a central point where you can always check the status of your system. Okay, and then another option is what we saw before with Dask Gateway, is that every user gets their own private Dask cluster. They have their group of workers, and they can run independently. Okay, another use case, which might be better in some cases, is you want to have one cluster only and have all the users connect to that cluster. Okay, and so there is a tutorial for this thing as well. Okay, then for a high energy physics project, I also deployed the capability of using CVMFS. So it's a file system distributed, which is used to deploy software. And you can even run, you can basically mount this across all of your Jupyter Hub instance, and you can have kernels running out of this system. Okay, another possibility is deploy a database. Okay, you can deploy a database in Kubernetes, and so this can be used by a Science Gateway, standard backend database for a Science Gateway, and then you can have the web part of your Science Gateway also run in Kubernetes. Then another feature is, instead of deploying Jupyter Hub, some people were interested in Binder Hub instead. If you ever used Binder Hub, is similar to Jupyter Hub, but it's more on demand. So generally, this is a they provide a button on a Jupyter notebook on GitHub, for example. So you host your, you have a Jupyter notebook on GitHub, and you want users to be able to run that notebook. And so you can have this button that you click, and this is going to spawn is going to build a container for you, and then execute that container. And so you're going to be redirected there, and you can run through that container. And so this is very useful for demo purposes. So you want some users to just be to have the capability of running something on the fly without having an account, or so it's a different use case than Jupyter Hub, but can be deployed on the same underlying Kubernetes. Okay, then we have services to back up nightly all of the data and monitor that. We have a service to do auto-scaling. This is a bit experimental still, so we want to be able to grow and shrink your Kubernetes based on how many users are using it at the moment. So basically it's a service, and the nice thing is that also this one is a service that runs inside Kubernetes itself, and is able to create more nodes or delete nodes that are not necessary anymore. Okay, and then I have the last couple of features which are still in progress. One is running Singularity. So you're probably familiar with Singularity containers that are commonly used in HPC. And one possibility is inside this infrastructure, you can also run, for example, Jupyter kernels running from a Singularity container. Okay, so some scientific collaborations are abandoning Docker and going to Singularity because there's for some of the features that Singularity offers that are not in Docker. And so I'm working on making this a possibility. And then another thing is now a weak point of our deployment is that we are using just one single master node. And so this is, so if you want to have a permanent cluster, you want to be sure that this thing is always up, then you want to have more than one master node, and so you need a load balancer to be on top of your Jupyter Hub, so that can distribute all the different calls that are coming in on all your different master nodes, and this is mostly done, so it's going to be available within weeks. Okay, so this is the overview that I wanted to give you. That's the link on the tutorial on specifically on Dask. With all the, and on there's the video, and there are all the Jupyter notebooks that are needed to test, to make all the different parts of the tutorial, and all of those was executed on one of these clusters. So, and during the tutorial, I also talk a bit about the whole infrastructure. And so, yeah, so I'm not part of Unidata, I'm not part of NCAR either. So it's difficult for me to understand exactly what are the possibilities for you to use this kind of services. So please, so I focus my talk on giving you an overview of what we can do. Please contact me. So I have specific funding from Jetstream to help people that want to deploy this. So I'm available for helping out. And so if you're interested in any of this, please contact me. We can see if your use case is suitable to be executed on Jetstream. I can even spend some time to deploy specific services that you need and to make them into packages that can be more easily made available on Jetstream. Okay, Thank you very much. Yeah, so I think we can go into questions. Maybe Jim?
First, yeah, thanks. I have a question about the NFS capabilities. Is that internal to Jetstream, or are you able to cross-mount this from remote machines as well?
Yeah, you can. Yeah, you can mount also from external machines. Yeah, then depends on the network, but yeah. So it's more reliable with NFS specifically. Yeah, having it local would be better, but you can also mount external systems into.
Just to follow up, I mean, let's say a use case, you're running some sort of model on Jetstream, and you want the output to go to a local disk. Is it faster to NFS mount your local disk, or Globus or something to get it back?
Yeah, probably Globus is the best thing. Yes, yeah. So you do your computation and you submit a Globus job to get the data back. I think that would be most performant. Yeah.
There's also a native CFFS feature in Jetstream. It's OpenStack Manila, which is file systems as a service. That is exportable outside of Jetstream. We generally guard that pretty tightly for security purposes. But for internal sharing, it's quite good, where you can. It basically is a shared NFS server to simplify it down, but it does all the management for you when you create a share, so you can just mount it on any and all of your Jetstream instances to share data between them.
Yeah, so I have a tutorial on Manila over there, and the tutorial of the NFS standard over there.
I'm curious about the use cases. About what's the breakdown for folks using this for fundamental research versus teaching, and if the latter, if it is, if there are folks using it for teaching, which I assume there are, how do they have any clue, like how many core hours they're going to use, and what do those allocation processes look like for those of us in academia that would love to use this for teaching?
Sure. So teaching is indeed a primary use case. I'm going to say that it's about 60-40 research to education. That's actually grown considerably over the last couple years. So it used to be probably 80 to 90% research, and then the remainder education. But a lot of people are finding to be an excellent place to teach, especially since you can teach with fractional GPUs as well and have real GPUs available to you. The process, how you figure out what you need, we have an estimator tool on our website that can help kind of figure out. So if I need a VM with 4 cores and we're going to have 20 students, we actually have a calculator tool that kind of helps you figure it out on the doc site. That said, if there's ever questions, you can always open a ticket and we can help you walk through that as well.
Yeah, if you look on my blog, I also have a simple Jupyter notebook that you can use to do some computation. So you see, you decide how much memory you need, how many CPU you need based on the number of students, and then you say, okay, I will need something like one. You see here number of instances. Some large and some medium instances, and then it's gonna compute the SUs for you. Yeah, so if you Google for Jetstream calculator Zonca, you can find it.
I also put the link in the chat. Of course, that doesn't help the people in the room, but hopefully somebody can grab all the links that I dropped in there and share them out. I dropped a whole lot of links in the chat. But the allocation process itself is fairly simple. Anything up to 3 million core hours, basically it does not go before the panel. So if you're up to 400,000, basically I'm the sole reviewer. If it's up to 1.5 million core hours, I'm also the sole reviewer. Up between 1.5 and 3 million, there'll be 2 expert reviewers along with me. But the paperwork burden for getting an allocation is pretty much on the smallest level. It's a paragraph. At the 1.5 level, it's a page. And your syllabus will suffice for that sort of thing if you're teaching. We want to know the course. We want to know how many students you're expecting just for forecasting purposes. But we've worked with Access over the years and Exceed to try to make it so it's not an onerous process for those that are teaching, because we want it to be so we get out of the way and you can do your work. Did that answer your question? Or
Thank you.
Yeah, and if you need any help deciding, for example, how much memory the users are gonna need, you can get in touch with me. I can help to give some guidelines on what's suitable amount of resources for standard process Python, depending on the kind of data that you analyze.
I have one question from the chat. Thomas in the other room is asking, can you discuss how full Jetstream is? And I'm not exactly sure what he means by that.
I mean, like what resources do we have available?
I am not sure. Thomas, if you can hear us, maybe jump in.
Yeah. Yes, we are looking for new users. Allocations come and go. So there are a lot of allocations that have literally been with us since the first days of Jetstream 1. Unidata is one of those. But then there are a lot of projects where somebody gets a grant and they have a year's worth of work to do. And then when they're done, it expires. If they get another grant, they come back. Maybe they don't. But we feel, we hold back about 25% from overcommitting anyway. So we can be on demand, because we are an on-demand resource. So we want anytime that a user logs in and wants a VM, that they'll be able to get it. We have plenty of capacity right now. In fact, I am surprised at how much capacity we still have left in our GPUs. I figured we would be 100% allocated by now there, and we're not. Large memory is surprisingly not as allocated as I expected. CPU is healthily allocated, but yes, we are always looking for new users. We are not near capacity, and frankly, if we get to the point where we're constantly at capacity, it makes us a strong use case for getting more capacity. So additionally, part of our grant is that we are supposed to have a no compete follow on to Jetstream 2. So we are a year and some change into operations. So we're going to have three and some change years left on this grant, and then we'll have another 5 years of next generation cloud after that. So we are looking for new users. We will be putting up a Grafana dashboard probably before the end of the year or early in January that will give you real-time looks at how busy the cloud is. The only reason we want to do is just for people to see how healthy things are at any given time, but there's plenty of capacity. Come on down.
A lot of people are more used to use traditional HPC, so they don't even think about deploying, instead try running on Jetstream. So it's more of a new, still kind of a new resource for science. So for that reason,
and for especially in this day and age, teaching anything with GPUs, finding GPU time anywhere is tough, and finding GPU time in commercial cloud is usually cost prohibitive to people teaching. So one of the things that we want to do is help the next generation of researchers, or the current generation of researchers that maybe don't have access to learn on GPUs. We do subdivide our GPUs using the NVIDIA drivers, so we can slice it down and get 5 slices per GPU if we need to, which is perfect for teaching because it gives you all of the ability to do any GPU programming without taking a full GPU per student. So we can get a lot of students on there for teaching purposes. And so if you have a GPU education use case, we certainly welcome you to come talk to us about it.
Any other questions, either in the room or out in the ether out there online? Dennis,
Can you tell me the relationship between Jetstream 2 and Swift, the Swift project?
Well, I mean, we aren't personally acquainted with them, but we have Swift available. Well, we have an object store available with a Swift front end on it. So we are not actually using OpenStack Swift, although we are using Ceph's Rados Gateway, which talks natively to Swift to allow you to do to do object store access. Is that where you're kind of going with this?
Yeah, well, we have a project here which is talking to Amazon S3. And I note that Swift claims to have an S3 compatible REST API.
It does.
And so I would like to extend our stuff to talk to Swift. But I was just curious if there's a, I don't know how to say it.
Use
I can access.
I
I get
almost
Jetstream-
discovered everything. Yeah, so you see, you can actually directly use, for example, the S3 CMD. So once you have, you can get from OpenStack, you can get the EC2 credentials, and then once you have the EC2 style credentials, then you can use all the standard S3 tools, for example, S3 CMD and any other. So everything is stored into the standard S3 configuration file. So whatever tool you have that reads those standard keys, then you should be able to do it.
Okay, my question actually, I think I can clarify it. Since we have a Jetstream allocation here at UCAR or at Unidata, can I use that to access Swift resources?
So, but the Swift resource is somewhere else?
I don't know. That's what I'm asking. In effect,
So
are there Swift resources available through our Jetstream allocation?
So Jetstream allocations in general, all will have the ability to talk to Swift to store data. So any allocation by default gets a terabyte of allocation. Julian Chastang holds the allocation for the Unidata Jupyter project. You could actually get your own independent. It's not by organization, it's by PI. So any faculty or staff member at a US-based institution is PI eligible. So you can get your own allocation, and then you could use Swift or S3 to be able to talk to our object store. If you want to move things between, say, Amazon and our object store, you can absolutely do that.
Oh, so you have an object store separate from Swift?
Well, Swift is just the front end. Swift is just
Okay.
the means of talking to it. It's not a protocol, but it's basically an OpenStack project that allows talking to S3 objects. So our Ceph storage pool is our object store, and Swift is the means by which you talk to it.
Okay, good enough. Thank you.
Yep.
Horizon interface to Jetstream. And so you see under object store, this is where you can create your containers, and then you can interact with those containers via the Swift API or the S3 API, and you can read and write data.
online, one last chance. Well, hearing none, let's give a big thank you to